Just here we go. Perfect.
Welcome everybody. This is the MS in Architecture Computational Technologies program at New York Institute of Technology. And we are honored here today to have our esteemed colleague, Aaron Sprecher, giving one of the great keynote lectures this semester. I'm going to introduce Aaron formally and then maybe some notes before we have Aaron's presentation. But I hope that you enjoy having Aaron with us. Aaron Sprecher is a Technion Faculty of Architecture and Director of Material Topology Research Laboratory and the co-director and founder of Open Source Architecture. Aaron Sprecher is going to give a very interesting presentation today in relationship to computational architecture. The title of the lecture is Instabilities and Potentialities, a keynote address on computational architecture. Computational architecture is inherently associated with the ability of a given design system to exchange information with its environment. Such a capability is a function of the intensity and extensivity by which information aspects impact the architectural objects, the way it is conceived, iterated, simulated, analyzed, and manufactured. The nature of information technologies entails three significant shifts in architecture today. Its movement from an abstracted mode of codification to the information of its image, the emergence of informed object as a statistical model rather than a fixed entity, and the increasing porosity of its architectural discipline to the fields of knowledge, to other fields of knowledge. These three conditions will be addressed across multiple research projects recently deployed at Open Source Architecture and the Material Topology Research Lab. These projects question the technological continuum between humans and machines while forming architectural environments that are ever more sensible, mutative, and unstable. Aaron Sprecher is an associate professor at the Technion Faculty of Architecture, where he leads the Material Topology Research Lab. In parallel, he's an academic director of the Center for Advanced Manufacturing at the Israel National Building Research Institute and co-director of the award-winning practice Open Source Architecture. His research and design work focuses on the synergy between information technologies, computational languages, and digital fabrication systems, expanding how technology informs and generates innovative approach to design processes. Significant publications, architecture information on the nature of information in digital architecture with myself, by the way, Lorenzo Iroa, Sprecher editor.
Exactly.
Radledge Taylor, Francis, 2013, a big achievement, by the way. Congratulations, Aaron.
Yeah, to you too. For me as well.
Adaptive Knowledge in Architecture, Sprecher and Arens, AD Magazine 2016, Instabilities and Potentialities, Arens and Sprecher editors, Radledge, Taylor, and Francis, 2019, which I also had the pleasure to contribute to. Craft Outside, Sheikh, Bar Sinai, Sprecher in Construction Robotics 2020, Robotic Tools, Native Matters, Bar Sinai, Shaked Sprecher in Architectural Science Review 2021. Adaptive Robotic Stone Carving, Method, Tools, and Experiments with Shaked, Bar Sinai, Sprecher in Automation and Construction 2021. All right, so now the informal introduction to Aaron. Aaron, of course, is a very good friend of ours. We have been doing a lot of projects together, and significantly, something that you did not mention in your bios, we did the groundbreaking Acadia 2010, right? That was, people still talk today about that conference that took us so much work to organize that, but it was, a very nice collaborative project in which we really did a lot of amazing things together, including an amazing party with the DJs that had a lot of consequences, if you want. But since then, the issue of information, I think that the research of Aaron, right, in relationship to information has been very relevant and groundbreaking since then and even earlier, of course. And I have the pleasure of collaborating in many different projects and following Aaron's career for many years. So it's very nice and we are honored for your contribution to our new program. Because not only because you're a friend of ours, and we wish you to establish future collaborations between your program and our program, which I see that you're doing amazing groundbreaking work, but also to see how we can continue the conversation in different structures and with different types of work in a way, right? So here we are with our students, and we welcome you. So thank you for joining us, and it's a pleasure to have you. So the floor is yours.
Well, thank you so much, Pablo, for the introduction, both the formal and the informal one. And you're absolutely right. 2010, the Arcadia conference together was for me definitely a pivot point in terms of the way I looked at architecture. I think that it was for us certainly a major experience. And so first, it is my turn to congratulate you and NYIT on the occasion of the launching of the Master of Science in Architecture and Computational Technology program. I think that it is a big step for the School of Architecture, a significant one. And I know how much you are key in the building of this program. So really, my warmest congratulations. I feel, especially honored, to join you, as indeed I had many opportunities to discuss the nature of technology with you. And I would, as I mentioned before the start of the lecture, I decided to craft actually a lecture that is closing 5 years of research at our laboratory at the Technion. I thought that that would be actually a way to share with you some of the ideas on how we are leveraging and using the master and the PhD program studies at the Technion within our lab, and how we are actually deploying research projects. So let me start by saying that many of the projects that I will present today stem actually from this discussion that I had with you, I like to say, for the past almost 20 years. So you see, it's a long way, but those projects are definitely inspired by our discussions. And I like to think that, in fact, the title of this lecture comes from, indeed, those three observations that through our discussion in multiple events, through our discussions, I think that those ideas about how the computation and how the digital tools are influencing architecture, at the end, they have shaped and produced a certain shift that I will discuss tonight. So let me see first how that works here on my end. Here we go. So here you see some of the recent pictures from our lab, from part of our lab at the Technion Israel Institute of Technology. And I will start with this. Information technologies have transformed the way we perceive our human environment. Prior to the last 20 years, information technologies were in fact considered outside of the architectural discipline, and architects who experimented with digital processes transgressed, or at least we saw them as transgressing, their disciplinary boundary. Pioneers such as Yona Friedman and Niklas Negroponte carried architectural knowledge into the realm of digital technologies to experiment and generate new knowledge from operating in an alternative context that offered new possibilities. These first moments of what we commonly call today digital architecture are of a high interest at our lab. The work of architect Yael Engelhardt, one of our recent graduates, exemplified this condition. Yael worked together with Yona Friedman in 2018, and they worked together really close by to reenact a software that Yona Friedman designed with the Architecture Machine Group at MIT in the 1970s. This software called Yona, Your Own Native Architecture, is in fact the ancestor of what we call today parametric software. Another example of such an interest to bridge architectural theory, history, and practice is this ongoing research by graduate researcher Tamar Levinger. Here, Tamar investigates a series of exhibitions that took place in the first days of the digital era. And the objective for her is to map and analyze the multiple discourses that appeared in the emerging field of digital culture. Observing these experimental years of digital architecture contributes, in fact, to the understanding of the profound impact of technology on the way architectural objects are conceived, iterated, simulated, analyzed, and produced today. In this recent book that you just mentioned, entitled Instabilities and Potentialities, together with our partner, Chandler Ahrens, we identified three main shifts in the way we approach architecture in the age of computation. First, its movement from an abstracted mode of codification to the formation of its image. In other words, this idea of scripting, of programming the machine in order to generate an image. The second shift is the emergence of the informed object as a statistical model rather than a fixed entity. The third is the increasing porosity of the architectural discipline to other fields of knowledge, what we commonly call transdisciplinarity. These three shifts in architecture are largely due to the current convergence of knowledge that is an opportunity to bridge historical and design practices, scientific and haptic modes of design thinking, and above all, local and global cultures in manufacturing and in designing. So I propose to discuss a series of research that are ongoing or that were recently completed at MTRL, the Material Topology Research Lab that I direct at the Technion Institute of Technology. And each of these projects reflect a particular relation to architectural history and practice. I will start with Dr. Tom Shackett, who recently completed his doctoral thesis at MTRL, a thesis entitled Technical Uncertainty Toward a Sensible Architectural Tool. Tom Shackett was the first PhD to join the lab, and together with him, we really built that lab. So to say that the importance of having partners as you are building an experimental research environment. Tom Shackett's outstanding work considers the potential of reenacting ancient modes of architectural manufacturing in the age of automation. His work addresses the need to communicate sensibility to robotic tool while shaping the object. So the story starts in Jerusalem, a city whose facades are covered with Jerusalem stones. Here, the Grabelski family runs the last factory capable of stone cutting and dressing. The disappearance of this industrial field in the region results from its competition with alternative industries such as ceramics and synthetic materials, but also a lack of skilled manpower and a loss of historical knowledge as reported by Tom Shackett. Our Middle East region has a long history of using stone as a central architectural element. Conrad Schick, for instance, an architect and archaeologist who worked in Jerusalem toward the end of the 19th century, described in detail the features of the chisel marks on the stone walls of Zedekiah Cave, one of the ancient quarries located in Jerusalem Old City. Another example is Tawfiq Kanan, a Palestinian doctor from Jerusalem and the director of the Hansen Hospital, that described the local construction methods with special emphasis on the different types of stone and the cutting tools that were then used. This legacy is still present in the Jerusalem master plan today. You can see a statement that says the outer walls and pillars of houses will be covered with natural, finely dressed stones. Today, the Standard Institution of Israel references traditional stone dressing method and provides a detailed account to the different patterns of stone finishing. As Tom Shackett reports in a recent visit to the factory, there were signs that in the last decade, the stone industry had undergone a transformation from manual labor to automation of production processes. Nevertheless, if one looks closely at the end of each stone processing procedure, there appears to still be a demand for skilled craftsmen to carry out complex custom tasks, as you can see here in this short movie. Considering the need to address the parameter of uncertainty in the craftsman's gesture and the unpredictability regarding the process material, Tom Shackett proposes a human-to-robot craft method that translates the craftsman's tacit knowledge, that is a set of skills and abilities that individuals gain by experience and that are often difficult to communicate. Tom Shackett proposes to envision a practice in which a robotic arm is taught to react to specific material scenarios, similar to the way craftsmen would. In his own words, this research extends existing knowledge in digital manufacturing based on the notions of technical indeterminism and sensibility. And so for each case study that he investigated, Tom Shackett employed a research by design methodology in which, one, he considered the action expressed with a tool or a method. Two, he produced specific objects. And three, he examined them as valid research outcomes. In short, what he's proposing is an alternative to the typical top-down approach that usually addresses the complexity of robotic fabrication with a bottom-up approach that arises as a result of specific material conditions by relying on accumulated human data and autonomous processing abilities of local sensors. Let me show you. In the first experiment, a brush tool equipped with pressure sensors is mounted on the robotic arm. It displays all the components of the sensory apparatus: a robot adapter, a flat paintbrush, and an open source load sensor. A custom developed real-time communication protocol mediates between the sensor and the robot. While the robot is the moving platform, the sensor is situated on the tool, and its purpose is to convey the material or environmental sensation back to the robotic arm. And that's what you see on that screen, where you see the pressure of that paintbrush on the paper. In a second experiment, aside from touching sensing, Tom explored the use of machine vision to produce real-time robot toolpath. Here we see Tom's collaborator, Uri Dubin, a neuroscientist who controls the robot using hand gestures. In a third experiment, Tom employed object detection methods to produce real-time robot tool path. While this is a complex task for the robotic arm, it is rather easy for a human. In a fourth experiment, sand is scattered on the table, and the robot is instructed to form it into a pie. This is a sort of an iterative process that gives that actually is going through analyzing the work of the robot. For every brushing cycle, the plan relies on generating a vector field, which is dispersed evenly across the sand geometry. The robot repeats the process until the desired result is achieved. Another example, 5 stones are placed on the table, and the robot is instructed to arrange them in a circle. For each stone, a vector is generated from its current location to its target location on the desired circle. These experiments provided a basis for developing the method and appropriate setup for the core experiment of the research. It mediates between the deterministic nature of the software and the sensible dimension of the fabrication tool. For that purpose, Tom Shackett developed Reflex, that is a grasshopper application capable of craft-oriented robotic fabrication by employing 3 primary capacities: image processing and object detection, computer vision and 3D reconstruction, real-time robot control, and predefined fabrication modules. In short, on the Rhino Grasshopper side, Reflex provides an agile framework for craft-oriented fabrication. It is organized around several capabilities responding to the challenges arising from uncertain material behavior. Reflex functions include the communication and data exchange protocol, Rhino geometry to robot command translation, input devices, image processing, and the core craft operations. Here, for instance, we see an integration of deep learning capacities into Reflex that enables the image classification for material analysis. Reflex computer vision module can also be performed for failure detection during fabrication. So the whole idea here is actually for the robot to really sense what is happening in real time as it works. Back in the Grabelski factory, a stone carver is removing the sharp edges of a custom ordered stone. His capacity lies in the sensitivity he applies using carving tools. Addressing this condition, Tom Shackett offers a unique research method for performing adaptive robotic carving. His method consists of three main stages: human-robot craft transfer, robotic tools development, experiments, and validation. This stage employs motion capture techniques to record and analyze gestures of craftsmen at work. In order to record the specific hand gesture of the craftsman at work, Tom Shackett used a motion capture system. The chisel is mounted with an adapter consisting of 5 markers. Each marker receives a unique ID that is, here we go, that is used to control the, Each marker receives a unique ID that is used to construct the adapter in 3D and derive the chisel's position and orientation in space throughout the carving session. And that's what you see here in this short animation. The documentation phase provides an initial database for analyzing the 3 carving techniques. Following each session, the trajectories were reconstructed and exported as 2-dimensional arrays in Excel format and visualized using Python. Lastly, Tom Shackett developed a computer vision application, allowing to detect the total amount of material removed from the stone surface for each chisel stroke. And he also developed and designed an end effector that includes a pneumatic hammer that connects to a variety of chisels, a linear axis that brings the chisel back each blow and replaces the second hand of the craftsman, and a shock absorber that prevents damage to the robot due to the stroke impact. And you see here the various elements that are forming this end effector. The robotic setup for the stone carving experiment consists of a large industrial robotic arm that is installed on a linear rail. The toolkit consists of a custom design multi-chisel carving end effector. Tom Shackett's PhD research on technical uncertainty explores the potential of craft-oriented robotic fabrication in the face of a decline in manual craftsmanship in architecture. Despite the growing availability of digital tools, they are in fact limited in their capacity to perform custom high-scale tasks. This limitation stems from the challenges presented by unstructured environments, material uncertainty, and the physical distance between the designer and the manufactured object. His research and subsequent patents extend knowledge on digital manufacturing, proposing to integrate sensory data and manual capabilities into architectural production using industrial robot as a platform. In his own words, it includes documenting the gesture of a local craftsman, augmenting a robotic fabrication tool with a custom end effector and sensor toolkit, and enhancing the fabrication protocol with material and spatial awareness. Such capacity does not rely on increased precision, predictability, or repetition. Rather, it is rooted in the ability to contain imprecision, handle uncertainty, and support variation. And so this idea of sensitivity, I would like now to propose to look at it at a much, much larger scale, at the territorial scale. In her recently completed doctoral research, Dr. Karen Lee Bar-Sinai engaged with the notion of technological sensibility and robotic fabrication at a very large scale, that is, the territorial scale. Her thesis first addressed the notion of informing grounds, that is, the capacity to shape grounds to a desired form of performance. In her own words, Karen Lee Bar-Sinai's work questions the notion of cultural landscape, or in other words, the significance of the human action on marking and shaping its environment. The MTRL setup at our laboratory for informing grounds is based on the notion of bridging scales, or in other words, the possibility of simulating ground formation at a laboratory scale while envisioning its capability at a territorial scale. These scaled experiments offers the possibility to test the relationships between the robotic motion, the tool, and the material at hand. For instance, in her work, Kerli Barsinai tested 3 kinds of tool path motions and their respective topographical effects. Shown here are tests on linear motion. Linear motion is a robotic action of flattening and creating divisions between different areas. This motion was most effectively performed using a simple white edge and effector. After doing 2 experiments using such an end effector, she produced a 3rd forming pattern that she considered to be made out of curvilinear motion, a robotic action aimed to form subtle undulations by employing a continuous sinusoidal toolpath on the ground. To support this process, Kerli Barsinai developed an iterative fabrication protocol for informing grounds. In testing the 3 motions, linear, pressing, and curvilinear, Kerli Barsinai concludes, first, subtle changes in the tool edge design produce distinctly different effects. 2, intricate effects can be attained by simple tools. And 3, limiting the tool shape to a single point or edge allows a higher degree of control in the sand forming process. Kerli Barsinai's approach to material landscape envisions the capability for reconstituting geomaterials, that is, defined as modulating locally found matter into construction material using robotic tools and additive manufacturing. In her work, she looked into a Negev desert site in the south of Israel and conducted mineral profiling for geomaterials drawn from it. That work included the mechanical and chemical analysis with the long-term goal of developing a recipe for a cementitious material using locally found aggregates. The reconstitution involved 3D printing performed by an industrial robotic arm equipped with a custom pneumatic extruding end effector. The extruder here is filled with mixtures of side sand and various binders. These strategies served as a basis for exploring procedural robotic fabrication, a robotic process which starts with earthworks and robotic ground forming through 3D printing of the elements on site, and finally with their assembly to a structure on the formed ground. In this context, Kerli Barsinai and her students and her team tested methods for constructing parts produced by additive manufacturing, discrete, or something that she considered and called discrete additive. For her, discrete additive means stackable discretely 3D printed wall elements. The elements are parametrically designed to be printed next to the site, manually carried, and then stacked in place to form the structure. The architectural system, as such, features an open roof structure composed of 3 layers of stackable hollow elements. The stackable U shape varied both horizontally and vertically, and stacking was to form walls, corners, and openings. So for Kerli Barsinai, it is here proposed a new method of additive manufacturing that is combining the conventional method of continuous additive with modular additive 3D printing of continuous segments on site. Or in other words, the idea of 3D printing on the site, forming those objects and then using those objects as sort of prefab elements that can be stacked and that can actually form the building. And this idea also brought her to develop a protocol for repositioning a robotic tool to produce such continuous segments on the site. And these continuous segments are overlaid with discrete elements in various forms, as you can see here in one of those catalogs that she produced with her students. Beyond the contribution of a fabrication protocol, Kerli Barsinai's doctoral thesis develops a comprehensive, qualitative comparative analysis between methods of on-site additive manufacturing And this is a major contribution to the field, as only a few research exist on such a question. So let's continue, let's pursue on this idea of locally sourced material. The work of PhD candidate Ofer Asaf, one of the new members of our lab. PhD candidate Ofer Asaf addresses automated fabrication processes by investigating the fundamental relation between design method, tooling, and material. Referencing the work of Keren Libar Sinai, Ofer first analyzes and reduces locally found aggregates to reach a particle size that would be optimized for additive manufacturing. Using an iterative method of testing, the soil-based material is combined with 100% environmental materials, including fibers, in order to reach a structural and mechanical property capable of sustaining its own weight. Ofer Asaf's approach to what he calls computing materiality provides a scientific context to define the multiple aspects that must be taken into consideration for additive manufacturing optimization. These iterative experiments provide fundamental data regarding the material behavior in additive manufacturing processes. Ofer Asaf's research stands at the crossing of quantitative and qualitative assessments of material performances. His research methodology provides the conditions to both consider the visual and physical behavior of distributed soil-based material and their physical properties that are key to any additive manufacturing processes. The control of additive manufacturing parameters, such as the distribution velocity, material elasticity, curing, generates formal effects that may influence the formal manifestation. The work of Ofer Asaf provides a scientific approach to the fundamental relation between tooling, material, and design in the formation of the object. Such an assessment is complex as it requires taking into consideration many parameters that are internal to the material composite mixtures, the type and design of the manufacturing tool, the method of material deposition, and the design definition of the object. Ofer Asaf currently optimizes this relation between design, tool, and material with the objective of producing in the coming year a full-scale construct that will dramatically leverage the environmental impact of architectural construction. More so, his current work stands among the few research that are today scientifically probing. And what you see here on the screen, by the way, is a 100% organic, natural material. You don't have glue in this, you don't have any kind of chemicals. Ofer Asaf, together with the MTRL team, and here you see research assistant Ronnie Hillel, who's been key to many of the projects that you've seen so far. They currently apply this fundamental knowledge to ongoing projects with partners from the Faculty of Civil Engineering at the Technion, Professor Arnon Bentu, a world expert in cementitious materials, and Oded Amir, one of the top scientists in the field of topology optimization. Here are some of our recent experiments on high-performance concrete mixtures that we investigate in partnership with the Israel Ministry of Construction. Our composite mixture and additive manufacturing method targets a reduction by 50% of construction material compared to conventional method of concrete casting. Concrete, very important. Concrete is the primary construction material in our Middle Eastern region. Our landscape is rich in minerals and aggregates such that cementitious materials are predominant in the construction field in Israel. The following research by graduate researcher Ryan Purati not only innovate in the field of concrete manufacturing, but foremost mark a paradigm shift for this industry. In this research, Ryan Purati envisions manufacturing very lightweight concrete architectural scale components using a method of rotational casting that conventionally belongs to the plastic industry. Ryan Purati's stunning research holds already by now multiple US patents and international patents. What you see here is in fact the first machine prototype that Ryan built about 3 years ago as he was completing his degree in architecture. This machine allowed him to manually produce his first proof of concept. The principle is to place a mold at the center of the two frames. The mold is then filled in with the material mixture. The material inside the mold is then distributed in all directions thanks to the force generated by the rotation of the two frames. Here is one of the first complex shape modules produced with Ryan's rotational casting machine. This concrete element is in fact a shell formed by a thin concrete membrane of barely 2 to 5 millimeters. So it is totally hollow and actually very strong. Subsequent experiments investigated the potential of including different types of fibers and textile in order to reach high-performant mechanical properties. Ryan Purati's research on architectural scale rotational casting addresses the required synergy between material definition, tooling, and design method. What you see here is a typical robotic setup that includes a zone for cementitious material preparation, a unique rotational casting robotic cell that we designed and that provides us with all necessary controls on the manufacturing process, and a zone for collecting the end product for validation. The architectural scale rotational casting method includes the use of molds that are designed for multiple use. And here, in this short video, you can see actually the multiple operations for producing these lightweight concrete elements. This video has been made at our lab, MTRL, and it is actually a research that we're developing now for the past few years in collaboration with the National Building Research Institute at the Technion. That is actually a governmental body that is working hand in hand with the Ministry of Construction and Housing. And here you see our team of technicians that are actually developing that concrete mixture that has a very high degree of phosphate in it to produce a very fast curing during the process. And it is actually the combination of that recipe together with the tool itself that provide us with the possibility of producing elements, architectural elements, architectural elements that are having very complex geometries in the lapse of a few minutes. You see here the robotic system at work. And all along that process, as you can see here, in that team of PhDs and masters, we are, of course, collecting data about the temperature of the material, about the mixture itself, the compositions, as a way to actually optimize the material, but always in relation with the manufacturing process itself. So the method, the material, and the tool are being looked in synergy. And so, as you can see there, by the way, a lot of the data is also dedicated to figure out the temperature of the material. You can see it here. That's the block, that's a concrete block out of the machine. We see the fumes because the chemical reaction is, of course, producing a certain temperature, and we are looking into tuning also the environmental temperature of the lab with the material in order to optimize that process. The objective of Ryan research is to ultimately produce an architectural structure made of customized thin-shaped elements. If successful, this project will offer a method of construction that is highly environmental due to its significant reduction of material use and labor-intensive operations. I would like to finish that project with this image because this is indeed our objective. Ryan and his team continue developing high-performance concrete mixture that would provide the most homogeneous distribution of material in the mold. You see here sections across prototypes using different material composites. From left to right, we observe a significant improvement in the distribution of the material under the impact of the rotational force. And so I believe that this is bringing us closer than ever to the production of what will be a full-scale mock-up. Now, let's leave the world of concrete for a moment and let's just go to look at very, very lightweight materials, such as textiles and fibers. Here is actually the work of a PhD candidate, Tamar Nix, at our lab. Tamar is currently working and developing her doctoral research in the field of industrial design. She's an expert in textile design, and she decided to actually look into the possibility of introducing textile within the architectural production. In the last years, in fact, there has been a growing interest in incorporating textile digital fabrication in architecture. While most research that combines textile and architecture deals with knitting, weaving, and yarn binding, only a few studies deal with the idea of crocheting, crochet. Crochet is a traditional handcraft of creating fabric out of a single yarn using a hook capable of achieving complex 3D textiles. So crochet, that is a technique for textile design, exists only manually. There isn't a single machine today that is capable of producing that technique simply because of its complexity in terms of the movement. This research aims to transform crocheting from handcraft to robotic fabrication, looking into its potential for architectural application. Computational crochet depends on three technological levels: mechanization of the stitch, computation of the pattern, and fabrication of a whole structure. So what you will see here are actually a series of experiments that Tamar has been developing with a research assistant, Ronnie Hillel and Doran Akash. And the idea here for her is to ultimately produce a full-scale mock-up that actually she completed about a month ago. So first, a few experiments. The experiments that you will see here concentrate on developing a novel approach for each tested craft. Here, Tamar Nix used a robotic arm that is actually very powerful, but also that has certain analogous, I would say, similarities to the human hand in terms of the movement and its capability and articulation. The robotic arm tool path expresses the yarn movement. There are in fact differences in the fabric tensile levels that you can see here in this first experiment of embroidery. And what you see here is, one of those textile that is trapped within a wooden ring. It turns out that that textile has different levels of tension. And what she's been doing here, while the human hand can easily negotiate those tensions, for the robotic arm, it is far more difficult, and it required to tune its power as it's actually creating the embroidery. In this second example that you see here, or experiment, Tamar Nix is looking to creating a woolen craft ball by having the robot working in the air, in the space, and distributing the yarn around a ring so that at the end it would produce a volume. What is very interesting in this experiment is that it actually offered her the possibility to design and to refine the design of such an end effector in such a way that the yarn would be always accessible to the ring and would not actually create some kind of a distortion in its movement. Finally, here, creating a yarn chain, so a crochet, is a significant milestone for crocheting using a robotic arm. The chain that you see here is the foundation and the starting point of any crochet handcraft. This experiment involved both linear and spatial movement. A designated crochet hook and effector controls the yarn movement according to the parametric toolpath. Among various positions of the hook, the short version appeared the most effective in terms of controlling the yarn. That's what you see on the right side. Finally, a last experiment that she did was actually looking into the idea of the most basic stitch type, what we call a single crochet stitch. Although this is a very simple stitch, it requires double insertion of the needle into an existing loop and 2 passes of yarn collection. This experiment involved a computerized model of the crochet base in managing the path accordingly. The crochet base was 3D scanned and incorporated into a Rhino file as a base for the robot toolpath design. So the idea here was actually to use a 3D scan of a textile in order to teach the machine to create the robotic toolpath. And that's what you see here on that screen. All these experiments led Tamarnix to produce her first full-scale prototype a few weeks ago. Here, the crocheting instructions were optimized using an algorithm that was provided by a group of researchers that are at the University of Pennsylvania and with whom we are currently collaborating. They are working on the computational aspect of it, and we are looking into the robotic condition of the crochet. Inflatable spheres provided the external tension that is required in order to hold the construction stable. Keeping the softness of the textile enables the full reuse of the material in different configurations according to specific needs. So again, the idea of creating a textile architecture for us has an incredible significance, I would say, in terms of its environmental impact, and I would say its impact during the construction. Here is, you know, a sort of a construct that can be easily built, dismantled, and moved to a different location. And I would like to end with 2 small projects, Pablo, if I still have time. But I think that you will be interested by this. Yeah, is that okay? Okay. Okay. These 2 projects will take us a little bit away from the world of fabrication, but I thought that it would be very important. The Material Topology Research Lab is indeed looking into the nature of multiple technologies. We're looking into fabrication, we're looking into haptic technologies, but we are also very much interested by the status of the image in architecture, or what is the representation that we are making in architecture. And here are 2 projects that are in some capacities related to that simulation and visualization dimension that we might find in architecture. This project here by graduate researcher Anna Boehm, and in partnership with Dr. Jonathan Dortheimer, who's a brilliant scientist and architect who's doing his postdoctoral studies at our lab. This partnership between them led them to develop a whole protocol that is entitled a machine learning approach to urban design interventions in non-planned settlements. Let me explain. This research by Anna Boehm and Jonathan Dortheimer suggests using machine learning as a method to read the complex morphology of non-planned settlements and generate new development alternatives that preserve the traditional knowledge of the local communities and promote their cultural sustainability. So what is very important here to mention is this idea that while we are talking very often about sustainability, we are often talking about it in terms of the environment. But there is another type of sustainability that is also recognized by the UN, that is the cultural sustainability. And here, I would like to take the case study of a town called Jizr al-Zarqa that is located in the center of Israel. Now, why that town? Historically, this town evolved in a spontaneous self-generation process for several decades. This town was born out of decisions by the citizens to build, but it was never actually amended to a master plan or by a governmental decision as to how it should look like. So it is a completely self-generated urban tissue and system. But then about a few years ago, officials decided to actually provide a master plan to the city. And that's what you see on the left, on the upper left side. It's a plan for a major development that, as you can see, goes in a very different language with what is actually the traditional way of building that city. So what Anna Boym and Jonathan Dotheimer decided to do is to actually investigate an alternative plan for that new development, looking into how they could actually be nurtured by the organization of that self-generated system in the Giza town. The suggested method is based on what is called a PIX-to-PIX model, that is a generative adversarial network protocol that was developed by NVDA. So they used that protocol for various applications of image-to-image translation, as you can see in the example here. And in this research, they use that protocol of the PIX-to-PIX in order to develop an urban design tool that is capable of learning and reproducing complex patterns that express the unique spatial qualities of that town of Giza Azarka. Above, what you see are several examples of Giza maps with varying complexities. Each of these were tested as training data sets for the GAN model, or for that computation protocol, in order to find the most suitable format for effective training. The purpose, the objective of the training process is to teach the model to fill in the empty part of the map based on the recognized patterns around it. In order to learn that, with each blank map, the model receives its equivalent full map. Each training dataset consists of 300 to 2,000 maps, depending on dataset complexities, and it takes several days for our powerful machines to train. On the training process, once it is actually completed, the model can be used on new maps to generate new urban fabric in the empty area of the map. Unlike the training process, which takes several days, the testing takes only a few seconds. Therefore, once the model is trained, it can be effectively used to produce multiple design alternatives, which can then be further evaluated. And so that's what you see here on this on this slide. On the right side, you see the original map. On the left side, you see what is the input, and in the middle there, you see what that protocol has produced as an option for building that empty space. As part of the training and testing experiments, the model, which was trained only on the morphology of Giza Azarka, that town, was tested on other settlements as well. So I knew I was coming to NYIT today, so we did a test on the plan orthogonal grid of New York, and you can see here how our machine would actually take and build a piece of that town in Israel in the middle of New York, if needed. But you see that the machine is negotiating with the New York master plan as well. The following slide demonstrates the way a machine learning model can be used as an urban design tool. The first image shows the current state of Giza Azarka, but then it is followed by 6 iterations of the model that generate new urban fabric based on the surrounding context and the existing pathways. And so now Anna and Jonathan are looking into what the machine has generated, and their next stage will be actually to compare that solution provided by the machine after being trained to the language of Giza Azarka with the master plan that is being proposed by the officials. And I will finish with this project that is very much ongoing, but a very, very exciting project at MTRL. This is a project that is being produced by PhD candidate Ethan Mann. Parts and certain aspects of these projects are actually being developed right now with in a partnership with MIT and with the Technical University of Berlin. It is called generative heritage. The UNESCO defines two different types of heritage: tangible cultural heritage that refers to physical artifacts produced, maintained, and transmitted between generations. A second type of heritage is called the intangible cultural heritage and indicates the practices, representations, expressions, knowledge, skills, as well as the instrument objects and cultural spaces associated therewith that communities, groups, and in some cases, individuals that are recognized as part of their cultural heritage. So there are those two different visions about heritage, the tangible and the intangible, the visual and the non-visual in many ways. Tangible and intangible cultural heritage are seen as separate entities of cultural heritage, and this is usually due because of technical limitation of recording them in conjunction. In this research, PhD candidate Ethan Mann wishes to follow the UNESCO 2008 Declaration on the Preservation of the Spirit of Place, reframing tangible and intangible as inherently linked, and develop the framework to preserve heritage as such. What lacks and what Ethan Mann aims to develop in this research is the technological framework to record and disseminate these interrelations. In fact, technologies allow us to probe the situated knowledge that resides in dynamic and contested memories. They have the potential to revolutionize the role of place in the humanities by moving beyond the two-dimensional map to explore dynamic representations and interactive systems. Digital media triggered an explosion of interest in narrative, linking tangible sight and stories. Stories are accounts of what happened to particular people in particular circumstances with specific consequences. And that constitutes a fundamental strategy for coming to terms with time, process, and change. In contested sites, and we have many of those in our region, there is a challenge that is to preserve the two aspects, the site and the multiple narratives. The game changer here is in fact technology. In this research at the Material Topology Research Lab, Ethan Mann develops techniques to capture both tangible and intangible heritage, site visuals and narratives, objects and traditions and storytelling, and he's linking them. That is his aim. Recording and analyzing the physical site through remote sensing technologies, collecting and analyzing stories using natural language processing techniques. For example, what you see here as some of the material that Ethan is currently working with. This is the recording of an ancient village of Lifta, just outside of Jerusalem, that holds layers and layers of history and stories of displacement, stories from multiple communities. Ethan is actually looking and retrieving data, visual data about that village that is today a village that is left over. And in parallel, he's also collecting narratives, and he's using natural language processing as a computational framework to teach a computer to understand the content of documents, including the contextual nuances of the language within them. The technology can then accurately extract information and insights contained in the document, as well as categorize and organize the documents themselves. In short, what Ethan Mann is claiming is that instead of looking at a site with the lens of a formal history, he's defending the idea of histories, the plural, the idea that there are multiplicities of standpoints and of narratives that are linked to a particular site. And he wants to report them and bring them together in a unique and single model. Through merging real and virtual worlds, and through the production of new environments and visualizations, extended reality technologies hold the potential to generate thick representations of locations holding contested, sometimes conflicting narratives. This means keeping the place, its archaeology, the memories that are embedded into it as a raw material, to connect these raw materials to different methods and networks, to allow the narratives of other times and people to be there, use the affordances of this immersive and interactive space of design. And you see here some of the students of Ethan Mann developing such model at our lab. And so here is for me to share with you the protocol that Ethan Mann currently develops as part of his doctorate studies, a method to generate a multi-dimensional database in constant evolution, a generative heritage tool, a living archive in many ways. And on this project, I would like to end, and I like the idea of an open end. I hope to actually come back and, in the near future and being able to show you, maybe with Ethan and other researchers from MTRL, to show you the results of their research. I would like to end with this image that is probably the most important one here. These are the researchers from the MTRL, from whom you've seen the projects today. Thank you.
Great, thank you so much, Aaron. Very nice lecture, very interesting research, and I'm actually very happy to have been able to schedule your lecture at this time, because many of the things that you presented we are actually working with. We're actually working with implementing machine learning in relationship to fabrication. So your advanced research is actually very, very interesting and very precise, but you're actually activating other notions that other people are not doing, which has to do with, as you put it, with characters of a local culture that perhaps escape the relationship, the typical top-down relationship. By the way, I don't know if you saw the studio. I didn't invite you to I forgot to invite you actually to our final review last semester, but I've been working with 3D scanning for 10 years now already. And we did a studio last semester, and the students here, Salma, Youssef, Kavya, and Farah, they did amazing work in terms of remote sensing, perhaps tangent to what you just showed in the last project, activating machine learning and VR. So maybe we should actually try to see points of contact, because Youssef, for instance, look at narratives from Egypt. So he did a 3D scanning project back there, and it's a very interesting subject that you're touching on. And also similarly, maybe it's another time for another conversation, but it's very interesting to see the problem of what you said about natural language in relationship to local histories, because I think that one of the current objectives that we have in our program is to deconstruct the Western history in relationship to data acquisition and 3D scanning, for instance. So we are actually working with, if you want, alternative cultures that have been somehow blocked by our notions of how to look at the past and how we can think in terms of the future. So it's actually it's a perfect timing of your lecture in relationship to where we're trying to go, and you are very advanced. I actually appreciate it a lot because I happen to know Tom, right? Tom Shakal is his last name?
Shakel.
Shakel, right? Like he came to New York with you, I think 3 years ago, probably.
It was like 3 years ago with Karen Lee, Barthelemy as well. Meanwhile, they completed their PhDs, and they collaborate for many years together. Now, let me say a few words about those ideas that that you are deploying and that you're presenting, that I think are really fascinating. Look, the very first thing is that first of all, I see myself as a representative of the lab, but definitely I think that and will be very happy for having the researchers themselves coming to you and lecturing. I think that they could certainly develop their projects in more details, and they will be very happy to collaborate. For me, of course, it goes without saying, but really just know that you have here a team of researchers who will be very happy to collaborate with your program and with the school. Now,
we need to find the structure, which is difficult.
Of course, but let me sort of relate on a few things. You were saying that we are very advanced. I think that the researchers are very advanced, and I truly believe in the idea of expertise. Each one of the researchers at our lab is really an expert in his or her own topic. They are really sort of spending many months and years developing those ideas. So what I decided to do today was actually to bring in, a sort of a taste of those various projects. It turns out that the lab started with this research that Tom Shaked has developed, and this idea of how you can bring the notion of sensitivity within the tool and within the computation of something. So this already then there was this idea that we should look at our tools as mathematical tools, but we need to find a way to make them sensible. So, so being able to work on those two, on those two aspects of, the mathematics and the sensible, I think that was for me a major step for what the lab decided, for what the lab became. Another aspect that I mentioned at the beginning of the lecture is the idea of history. I think that we are now beyond, these sort of exhilarating years of digital tools. So we are living with those tools. They are part of our life, of our culture. They are all around us. So the question now is, so what do we do? And that relation with history, I find it actually very important. So to give you, an idea of one of the questions that I ask myself all along in those projects. So you having tools in your lab, and it turns out that I probably have very similar tools in my lab. And my question then is how can we make sure that what you are producing is different than what I'm producing? And I think that the difference will come through culture, because we are coming from different cultures. We need to make sure that the robotic arm, the orange robotic arm that we see everywhere, okay, will actually perform differently and produce different results because of the humans and because of the cultural context of it. And so I find that really, really important. So as much as I'm fascinated by the global culture that technology is producing, this idea of the convergence of knowledge, I think that we need also to find our specificity in what we are doing. And for me, the specificity comes from the local cultures. So to give an example, just in general, okay, I really like wood. I would love to work with wood, okay, but I need a very, very good reason to work with wood in Israel, because there is no wood in Israel. We don't have wood in the Middle East. We have stones and we have minerals. And so just that makes already, a difference between us and, I would say, a researcher in that field in Switzerland or in Canada, for instance, you see? So I'm very much interested by that.
So no, this is great. And this is one of the reasons why I wanted to invite you to give a lecture, because I think that, that I think very differently and you think very differently in relationship to, let's say, the typical technologies that for instance, that we usually cross paths with. And you mentioned the issue of the tool. Everybody has a robotic lab and a robotic arm, right, in it. And that's one of the reasons why I was telling you before you started the lecture outside the streaming, that at Cooper, first because of lack of funding, but second because of an idea of authorship that we raised, at least I was, in a way I presented the counter argument to Mario Carpo, right? Mario, I think because he doesn't really, he operates from a history theory point of view, he would disagree with me about the notion of authorship in relationship to machinery. And that's why we actually develop our own machines, right? Like which is what you're doing also with the scripts. Like Tom, you were saying, is developing a new set of tools in Grasshopper. And that's one of the objectives of these programs, that each student develops its own, in a way, like very similar to what you're doing, its own technology. And I think that what you're saying about the site specificity and the history specificity, like the difference between being in Israel and not having access to wood, that's something that also comes from Latin America. Like the notion that you are going to do architecture with what you have. You don't bring things from China, or you don't activate a larger global, if you want, trade, because you work with the resources that you have. And I think that in the US, that notion, it doesn't really exist, right? It's a very different way of working. And I was going to ask you, because you were working in Canada, right? In McGill, and now you're working in Israel. But in a way, you started answering the question. But do you want to say anything else about that difference? Are you more comfortable with your lab in Israel, or what do you miss about working in Canada? Yeah, let's say.
No, well, the building a lab in Canada, that's something that happened actually closer to the year 2000. That was a time where we were really discovering those tools and trying to figure out what was their potential. Today, we know much more what are the potentials of those robotic tools and computational protocols. And so I think that the context is different. I think that the major difference indeed is that while the first years of robotic fabrication were very much related to looking into what that tool would be capable of doing, today we are much more, I think, concentrated on, or much more specific in terms of what we are searching for and what we are hoping for. Now, I will give you an example for this, because I mentioned it in my lecture, but I think that it is actually important. So everybody is today talking about 3D printing, everybody. And everybody is now the new trend is actually full-scale 3D printing, that as an example. But whenever we work very much, our lab works very much with the industry, and we are having a lot of meetings with industrial partners. And when we talk to them and we say, oh, so you are building a house, 3D printing a house with concrete. So explain to us, how you do that. And then they're telling you automatically, well, we have a concrete mixture, we have a material, we know how to do it, and here we go, we do it, and that's it. And whenever you try to get some data, some scientific proof of, let's say, the strength of their concrete, is their concrete really environmental? Is it really so that they are reducing the percentage of construction material when they're using that in a 3D printing process, etc.? Impossible to get the data. In other words, I think that we need the role of our academic labs and groups, and the role of our research is actually to to display, to share knowledge, and to share that knowledge with the scientific community in such a way that we can actually scientifically probe what we are saying. And so I think that that's actually one of the things that we're trying to do in our lab. That's probably the difference with the first years of robotic fabrication, where we were simply trying to make something out of it. Today, I think that we can really reach a much higher scientific degree in the research.
So in a way, you're saying that the also the cultural context change in terms of validation. Right?
Yeah.
But I want to leave the students to ask you questions.
Sure.
Because, you presented a very interesting research, and was heavily based on the students' research, and I want them to think like the way that you're making your students think. So, what do you guys think? Any reactions? Any questions?
And I like what I see on the table.
We're actually optimizing 3D printing with G-code. So we're trying to actually address exactly what you're saying. in terms of structural optimization and material reduction. That's one of the objectives of the studio this semester. But guys, any questions? You have to, like, what do you think? Or like reactions, thinking?
Everything is very impressive.
Can you hear Aaron, Youssef?
Yeah, I can hear.
Everything, congratulations on everything. Everything, like each and every project was very, very interesting. We're usually not that into, I'm not gonna lie to you, we're not that into lectures, but like this time was really, like I can see my my colleagues here. It was mind-blowing. And I would like to ask you if, because each and every project had a different approach. Do you have, like, do the PhD students come with their own projects, or do you have projects already and they come and build up on them? Because they were very different and they had it's a different spectrum. So.
Oh, great question. And I will be very pragmatic. I will explain the process. Okay. Because you know, what is your name?
Youssef.
Youssef. Okay. So Youssef, here is the way it works in our institution. So whenever a graduate student or a PhD would like to join the program, the student is actually a candidate and must go through a committee. The committee is actually the whole school. All the permanent profs are sitting in the committee, and we are reviewing the proposal of that student. So a student or a future student has to actually propose an idea, something that he or she wants to develop as a research. To produce this document, it's a document of 6-7 pages. Usually, that student will actually go and approach a supervisor because of an interest in the field that faculty is developing. And together, the student and the advisor are actually crafting that proposal before submission. So the reason why I'm mentioning this is because already then, the student did not even start yet the studies and the research. Already then there is a sort of a dialogue that is being established as to, where do you want to go with this? Usually I can tell you that it starts from a white page and we don't know where we're going. We just know that we have a certain ideas of things that, that we might investigate. And then, some readings. We look into some articles or some chapters of books, and by that channel, we just write that short proposal. We call it for PhDs in our institution, we call it a field proposal. For master, it's called a research proposal. What will be the research? And then the work starts. For masters, it's about it's an MSc program. The graduate student will be doing research for about 2 years. For PhD, it's a
it's a life.
No, actually not.
Is it short?
Yeah. No, the technion is very, very organized. It is altogether maximum 5 years, but like usually 4 years.
The PhD in Colombia, sometimes they last 9-10 years.
I know. So that's why I'm saying we are very, very strict on that end. But you see, Youssef, that's the I'm sharing that with you so that you understand how basically the dialogue starts. And then, of course, lots of experiments. We do experiments, and I can tell you that most of the projects that you see here. When we started working on that, we had no idea that we were going there.
That's what's great. That's what's great. That is that I can tell, and that's why I think that we share, Aaron, a common interest in computation. That in that sense, I think that we are very different from other. And your program is very different, and my program wants to be very different in that sense. That usually people just project what they want to do, and we don't have that problem. I don't have that problem, right? It's an open-ended exploration, and I think that's the best thing that you can do in a way.
Yeah, well, Pablo, you're right about that. it's not always coming from the side of the student or the researcher. It's not always that the researcher is coming and saying, well, you know, I have an idea and that's what I want to do. Very often it also happens that in this dialogue, suddenly the researchers say, hey, but what you are talking about and what you want to develop is exactly what I want to do. And then, you know, the dialogue is happening, you know, at the end, it doesn't really matter who had the first idea. It's just happening as a collaboration.
And you know, I want to tell something to my students, because they think, and this is the you know, something that we had at Cooper Union very clear, because they think that they come to a program like ours to learn something and, you know, and apply it, right? But I want to resist that notion, actually, because the notion of research that you're talking about, right? It works both ways, right? Like you know, in the notion of research that you're talking about, the student is equally active in the program. It's not just passive receiving information, but the feedback of the student is essential, right? That's why I actually like the fact that they are very few. We start, you know, when we had the COVID problem and some students could not come because of the visa. And actually that worked to me very well, because in a way, you know, we have the opportunity to be very precise and very deep about certain issues. And I have the feeling that in a way we are playing with their minds, and I think that we already started the damage in a way, you know, like we are.
Well, it depends. You know, you know. I mean, the reason why I end up the lecture with, you know, a view of everyone who's in that lab and developing this is because at the end, I have to admit, I feel that I'm one of them. The lab is really built as a puzzle of projects, and the dialogues and the discussions that are happening in the lab are often happening in between projects, actually, you know. So when you talk about machine learning for a minute, let's talk about machine learning and AI. Now, these are very, you know, I don't use the word AI in architecture that much, because it's very difficult to define.
I lost the game in that, because everybody says AI in the US. So now I also have to say AI, right?
Well, it would be more. I think that it is more accurate to say machine learning, because what we do is that we are trying to bring data, and sometimes very large data sets, to a machine, and the machine is being trained. So I'm quite fascinated by that condition. And I think that the fact that you are developing that in the context of fabrication, that is, I think, absolutely, you know, that's groundbreaking. And the reason is the following. And, you know, Pablo, we discussed that many times, and so I share that with Youssef and with the students. Look, usually what we know is that the fabrication processes are linear. They're like a sequence. You have someone designing something on the machine, then that person is sending that to a computer. There is a slicer that is actually preparing the file, and then it goes to the machine, and whatever is being produced is being produced. In some of the works that you've seen, especially the first project of Tom Shaquet, for instance, the robot is cutting the stone by itself. The robot hasn't been told to cut the stone. The robot in that case is literally sensing the material and making decisions. So whenever you put the stone in front of the robot and it starts cutting and chiseling the stone, actually we don't know what will be the result, because the robot is taking decisions. That condition, I think, is very interesting.
Yeah, because it's open. It's a very different way of working, right?
Yeah. Well, I think that potentially that means that the machine is really becoming an active member of the design process. Like, well, the machine.
That's what Negroponte, right, anticipated, and I think that now we are finally at that moment in which we can start addressing design in that way. And that's, I think, problematic for designers also, right? Which is what we were, I think that what we were discussing in Acadia 2010, what is design, right? But Farah and Salma, any? Farah, are you? Yeah.
Nice to meet you, Farah and Sana.
Thank you. I'd like to ask a philosophical question, which is, so if the construction and fabrication is this standardized, for example, here in America, would it be possible to bring in like culture? How would you're saying culture could bring specificity to the project or construction? Would I like bring in my culture here?
Sure. There's something really fascinating about this idea that of an architecture that would be somehow influenced by the local culture of the site and the context, being, by the way, not only geographical, but that can also be a cultural context, as well as the cultural context of the maker. And that, that would, in a way, I would like to use that image that I showed you of what happens when I say to the machine, here is the village of Jizar az-Zarqa in Israel, and I'm building it in the middle of New York. And then you see the machine is starting to, in a way, vibrate between two different realities. And you see that it wants to do something that is New York, but at the end, it also wants to do something that comes from Jizar az-Zarqa in Israel. And I don't know if that's, if that's what you mean, but there's something quite fascinating about this in-betweenness that you would see between cultures. The last project of Ethan Mann about the multiplicity of narratives that are related to a site is exactly that. You have a site and you have different people who've been living on that site. They're coming from different communities. They're having different cultures and they have different languages. And they all remember something different from that site. And what we want to do is to be able to build that model that is, formed by that multiplicity of cultural influences, and see how that model is actually deeper than what you would call a formal model coming from, an official history or an official narrative that is always one-sided about a certain site. You see, so let me first say that I identify myself very much to your question, and I think that it is absolutely crucial that whatever are the experiments that we are making, that we would be also capable of tracking those cultural conditions, because they are really forming in the making of the project and the research. Does that answer your question in some ways?
Thank you.
Salma has a question also.
Thank you so much for the presentation. I think that all of these projects are very interesting, and I'm looking forward to see more from your lab. I'm particularly interested in how all these projects have something common, which is culture, and how technology is used to recover the genius loci, to recover the local know-how and local material in the context. But as you mentioned, for the robot carving the stone, I was wondering, in your opinion, where do you stand in the design and research process, and moderate between the results emerging from the study of the culture and the context and from the results that are mainly produced by the machine? Like in other words, how do you keep your authorship as a researcher and a designer in the research processes?
Wow, that's indeed.
You see, we have good students here. Eh?
Yeah. No, these are really wonderful reactions. I really appreciate that. Like, really appreciate that. Let me first say something about the genius loci and about that idea of the cultural landscape that you mentioned. and the identity of a, you know, of a site or of a location in terms of its culture. I've been following for many years the research of Pablo on topographies, and in my opinion, that work on the topographies of, you know, on studying the surface is a way to extract that sort of essence that is also a cultural essence. So this idea of a cultural landscape means, how do I look at a site, at the landscape, at the terrain, and I relate it to a certain culture? The landscape being actually human-made and being actually a construct that the human is making, and it is actually the influence of its own culture. So I'm very, very much interested by that. I think that that could be maybe one direction that we can take. But now the question of authorship. Now, you're absolutely right that in many ways, we are putting our capabilities, or the capability of the craftsman, in the hands of the robot. But what actually was interesting in this case, for instance, in the case of the stone cutting project, is that while training the robot by recording the gesture of the craftsman and extracting those movements, bringing that to the machine to be trained, we suddenly came to realize, I haven't shown that, but I will definitely, Pablo, I will send you guys articles, PDFs that you can just read in your own time, and you will see some of those images. But we reached a point where the robot was inventing its own style of cutting. Because if you remember, for instance, in the city of Jerusalem, there are very particular patterns that are defined by the municipality in terms of the Jerusalem stone. It should be dressed in this way or this way. When suddenly the robot was capable of creating more patterns and other effects on the stone. So the question of authorship, I think that suddenly we see a displacement of the authorship of the architect or of the designer that goes in the direction of designing, for instance, the tool. And designing the tool, that really is part of the authorship. We have those things patented. Our names is on it. Okay, so that's how we claim authorship. But interestingly enough, it is also an act of design to manufacture a tool. And I think that one of the most beautiful conferences that I've been to in recent years was actually a conference organized by the European Architecture History Network, so historians, where they had a conference on it was called the Tools of the Architect. It was a whole conference about the history of tools in architecture. So there was a whole history of that. We've been always inventing tools. And actually, that's what you guys are doing right now in the lab. And in that sense, I would like to say that you are doing the most architecture act ever by doing that.
But you remember, Aaron, when we did Acadia 2010 and I presented the problem of authorship relative to the software designer, they were all very upset about it. Yeah, our colleagues, right? The architects, they were, but the software developers, they were actually agreeing with us, but the architects were not, right? And I think that that's when the crisis started emerging, right, in a way. Or at least a declaration of because it has been happening since, there's a lot of architects that actually became software developers, right? 1980s, whatever. So, but maybe it's a good time to conclude because otherwise we run into trouble. I mean, I wish we should actually, if we were in person, we would go for dinner or something, continue the conversation.
For sure.
But here we are with the time schedule, and we're going to be beyond our commitment. But thank you, Aaron, so much. It was congratulations for the amazing structure that you are creating there with all your PhD students and the master students. But I think that it's amazing, and I see that you're comfortable there. You're happy. You move back to your hometown, but you're actually doing groundbreaking work, right? Which is what matters, right?
Yes, yes. And let me just say that for me it was a pleasure to share those works with you, Pablo, and with you all in the group. And just that you know that you are most welcome to come and visit us, and we'll make sure to come to visit you. And definitely we want to partner.
Exactly.
Pablo, we will
talk
pursue on that one.
Exactly. Well, thank you so much, Aaron. Take care.
Thank you.